All right, so let's determine the value of this integral. Clearly, because the denominator is all real, we could take a shortcut and view this as the real part of the integral from negative infinity to infinity of e to the 2ix divided by x plus 1 squared plus 4. All right? As always, we'll symmetrically go along the x-axis and then we'll close the contour above. Here, we had to close the contour above because it was e to the positive 2ix. We've got problems at negative 1 plus or minus 2i. Jordan's lemma assures us that the arc at infinity will not contribute in the limit. And therefore, this is simply equal to the real part of the loop integral over this closed loop. That's equal to the real part of 2 pi I times the residue of e to the 2iz divided by z plus 1 squared plus 4 at negative 1 plus 2i. So that's equal to the real part of 2 pi I times, all right, this is a simple pole. All right? So that means we simply have to take the limit as z approaches negative 1 plus 2i of z minus z naught times this function. The easiest way to view this involves L'Hopital's rule. Remember, since we have a z minus z naught in the numerator, if we don't take the derivative of that part, then it will vanish when we plug in z naught. That means that in the numerator, we'll just have e to the 2i negative 1 plus 2i divided by, in the denominator, we're going to take the derivative and it'll be 2 times z plus 1. Z plus 1 is 2i. So this is our integral. So I'll get pi over 2, and then the real part of e to the minus 4 minus 2i. The real part of this, of course, is going to be pi over 2e to the 4th times the cosine of 2. Notice that as a nice byproduct of this process, we also immediately have the integral from negative infinity to infinity of the sine of 2x divided by x squared plus 2x plus 5. That's equal to minus pi over 2e to the fourth sine of 2.